Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at applications of breadth first search and looking at how to apply it to topological sort. So, just to recap, a graph is a set of vertices V1 to Vn, and we have been given as edges which are sets of pairs of vertices. The graph is given as V comma E, and if uv is in the edge implies vu is in this edge, then it is called an undirected graph. Sometimes the weights are also assigned to the edges. If there is an edge from u to v, we say v is the neighbor of u, and the total number of neighbors that are there of v is called the degree of the vertex v. For example, here is a graph. So, a graph is usually represented as a pictorial form. The vertices are represented as circles, and the edges, which are a pair of vertices, is represented by a line joining these two nodes. For example, here I have the set of vertices, and then I have these edges a b, b c, and so on. So, this implies that a b is an edge in this set E, b c is an edge in this set E, and so on. And A C, since there is no edge between A and C, the A C is not an edge in this graph. We can also have weights on these edges, and we can also have some arrows which basically denote directed graph. Means if there is an arrow from D to A, means D A is in the set of edges, but A D is not, because there is no arrow going from A to D. So, this is what we know as the directed graph, and this is exactly what we will be using today. So, the advantage of graphs is that it is a very mathematical way of expressing relationships among objects. It is very general and simple. It has lots of applications. In particular, many real life problems can be converted to graph theory problems, and thus studying the structure of graphs and designing algorithms is a very important subject in this field of algorithms. Among the various important concepts that a graph has, one of them is known as the connectivity of a graph. So, if there exists a path from u to v, then we say that u is connected to v. In an undirected graph, if there is a path from u to v, then the path from v to u, and so there is no confusion about what is connected to what. So, if u is connected to v, then v is also connected to u, and the set of all vertices that are connected to a particular vertex u is known as the connected component of the vertex u. A graph can be written as a disjoint union of connected components. Some of the most important problems or basic problems that can be asked is that given a graph G, is this graph connected, or given the graph G, is there a cycle? A cycle is a set of edges or a path that starts from a vertex and ends up reaching that vertex only. Also, one can ask questions like, given a graph G, can you find a spanning tree? Now, a tree is a vertex, is a graph which has no cycles, and if a tree touches every vertices of the graph, then it is called a spanning tree. It can be seen that if a graph is connected, then there exists a spanning tree. So, to answer all of them, we can use depth first search. In the last lecture, we have looked at mostly undirected graphs, but this depth first search can also be done for directed graphs. In directed graphs, things are a bit more trickier. If u is connected to v, that means that there is a directed path from u to v. But if there is a directed path from u to v, it is not necessary that there is a directed path from v to u. So, if u is connected to v, it is not necessary that v is also connected to u. A cycle is a directed path starting from a vertex and ending at itself. If a directed graph has no directed cycle, then it is called acyclic, or basically acyclic means there is no cycle. And here also the concept of connected components is very not clear, because as I told, if u is connected to v and v is connected to u, these are not if and only if condition. So, if a u can be connected to v, but v may not be connected to u. So, we say a set of vertices is strongly connected if for any pair u v there is a path from u to v and there is a path from v to u. So, the same set of questions can be asked now for the case of directed graphs, that given a set of edges, is u connected to v, is the graph acyclic, and find a directed spanning tree. What is a directed spanning tree? A directed spanning tree is a spanning tree where all the edges are directed away from the root. Since in a tree there is a unique root, so we can say that there is a unique path from the every vertex to the root. So, this path should be directed downwards. So, basically a directed spanning tree, for every vertex u, there is a path from directed path from the root to the vertex u. And again the answer is that for all of them the answer is the DFS, or the depth first search. Now, let us quickly see the depth first search example in the case of the directed graph. So, here we have a directed graph and we have this stack, and let us start from this vertex h. So, we want to do the direct DFS from the vertex h. As soon as we get this, see a new vertex, we color it blue and we put that vertex h on top of this stack. We maintain this stack on the left hand side, on the right hand side, which kind of is useful for our understanding of this DFS algorithm. Now, we look at all the neighbors of h. As soon as we find a neighbor, which in this case is g, similarly we look at all the neighbors of g again, say we look at e, and again since e is untouched till now, we colored e blue and we put e on top of the stack. Now, we look at the top element in this stack, which is e, and we look at one of the neighbors of e. So, what are the neighbors of e? Note that f is not a neighbor of e, because there is no edge from e to f. There is edge from f to e, but there is no edge from e to f. So, neighbors of e are c, b and d. So, we pick up one of them up, say in this case we pick up b, and again we color b to be blue and put b in this top of the stack. We look at the topmost element in this stack, which is b, and again we look at its neighbors of b, which in this case is only a. And now, we come to a, we colored a blue and put a in the top of the stack. Now, this a does not have any neighbor, although there is an edge from d to a and an edge from b to a, but there exists no edge from a to d or b, and thus a does not have any neighbor. So, a is kind of done, and so we will color a red and remove a from the top of the stack. We come to b and we see that again b does not have any outgoing edges, and since b does not have any outgoing edges, so b is also done with, and so we color B to be red and we move B out. We come back to the top of the stack, which is E, and let us look at the neighbors of E. Again, the neighbors of E are only C and D. So, we pick one of them, say in this case say D, and we look at it. Now, for D, D does have a few outgoing edges. For example, it has the outgoing edges to A and B, but as soon as it sees the edge to A, it realizes that A has already been marked, and so it will not select this edge. Similarly, it goes to the next one, which is B, and it does not select this edge. An important thing to note is that this edge is from a blue vertex, which is currently being used, to a red vertex. I will come to that in a short time. So, now say D is done, because D does not have any more neighbors to search. So, we will mark D as red and E as blue. Now, again look at the next neighbor of E, since it is in the top of the stack, and we see that okay, C is one of such things. Now, C was unmarked, so we put C on top of the stack and colored C blue. At this point, the top of the stack it is C, and we see that there are two edges going out of C. We look one of them and we see B. Now, again B is red already, and so this edge B should not be taken. It has one more edge, and that is this edge to G. Now, the edge C G is very different from the edge C B. Why is it so? The reason is that this edge C B is an edge to the red edge, whereas this edge C G is an edge from a blue edge to a blue edge. One might say that what is the great deal about this blue edge and the blue and red vertex? The idea is that this blue edge implies that this blue color implies that this vertex is still active. I have started from this vertex, gone and looked at some of the vertices that are reachable from this blue vertices, and so for example, this vertex C, there exists a path from G to C, directed path. Now, this path from a C to G would imply that I would have got a directed cycle, whereas if we had looked at this B, B was not blue, it was red by the time C looked at B. So, that means that B was not active. In some sense, B has been done with. All the vertices that can be reached from B has been looked at and completely sorted. So, there is no way that there is a path, there is cycle that B participates in. So, this kind of edges are very important in the set of the DFS. So, anyway, we can complete this algorithm now. Let us see all the edges have been looked at. So, we remove C from this stack and color it red, and similarly we go for this edge E. Then we go to this G and we look at a neighbor of G, which is F. We look at both of its vertex edges. Note that all the edges are to a red edge, a red vertex, and then slowly we will remove it and we have got this. An important thing here is that at the end, if all of them are colored, that means all the vertices are reachable from this vertex V, from where we started it. The other parts are that there are three different edges, namely there was the tree edge, cross edge and back edge. We will take a short break now. We will come back and look at it in a much more details after the break. Welcome back after the break. So, before the break we looked at the DFS algorithm, and note that in this DFS algorithm we had three kind of edges. Let me draw some. So, if say this was the DFS algorithm, the tree that DFS algorithm output. So, these are, think of them as the selected edges. So, these are the tree edges. Now, what are the edges that have not been selected? First of all, note that all these edges are directed downwards, because they are all directed. Now, what are the edges that have been not been selected? Are the ones that goes from, when I was looking at here, there are two kind of things. Say maybe when I had finished this part, then I was looking at this vertex, and there is an edge from this vertex to this vertex. Of course, this vertex is already done with. So, by that time this has all, imagine that all of them has become red. So, this has all become red, they all been done with. And now we have found a edge between here to here. So, this kind of thing is called a cross edge from a vertex to a red edge. Clearly, there cannot be a cycle here, because this goes down, there cannot be a, although we can use this one, I cannot go up from here to here. So, this kind of stuff are called the cross edges, and cross edges does not contribute to a cycle. But there is another kind of edge. Say I have been looking here. So, this is right now green. So, I am looking at here, and then I realize that, oh, there is an edge from here to here. Note that this one has been looked at, but not done with, because we are still looking at its all the vertices that are approachable from there. So, once we have this kind of a edge, this is called a back edge, an edge to your ancestors, and this kind of edge of course creates a cycle, because there is a path from here to here and there is a path edge going down. So, the back edges are something that creates a cycle. It is very easy to keep track on which one is a cross edge and which one is a back edge, but more importantly, this basically says that if while doing the BFS, if I encounter any back edge, that means that I have got a directed cycle. What is the running time of the algorithm? It is same. It is, as we have discussed last time, it is order V plus E. Now, let us look at a very different application of DFS, something that would not follow immediately. Say you have to do a lot of work. There are 8 different kind of works that one has to do, but there are some rules. So, these works are say A, B, C, D, E, F, G, H. Now, what kind of works can there be? They can be things of the form getting ready for office. How can you getting ready for office? A can be waking up, B can be brushing your teeth, C can be having your food, D can be wearing your clothes, E can be taking bath, and so on. But now, this kind of things has some kind of ordering, correct? For example, you have to brush your teeth before you have your breakfast, or you have to take bath before you wear your dresses, and so on. So, this kind of ordering exists. And now, a question is that can you come up with some sequence that, okay, let me do this way, and then I would satisfy all of them, like wake up, then I will brush my teeth, then I will take a bath, and then I will eat my food, and they will get dressed. This is one possible ordering. The other possible ordering can be, okay, wake up, then brush your teeth, then I have food, then I take a bath, and then I wear clothes. So, there are various kind of ordering that one can think, but as long as they maintain the structure or the rules. So, here I have just given some set of rules, say it is an abstract way of representing this problem. Let us say this job A must be done after B and D, job B must be done after C, D and E, job G must be done before E and F and after H, job E must be done before B, C and D, and job F must be done before D and E. So, give an ordering of the jobs. So, give a one sequence in which I can follow it, and I will not break any of the rules. This is a very important concept in so many things. For example, in the car manufacturing industry, there are so many small things that needs to be worked out, like you have to make the engine, you have to put the engine inside, you have to paint it, you have to put the seats inside, you have to put the tires, you have to put the steering wheel, and so on and so forth. There are over thousands and thousands of small jobs that has to be done, and there is an ordering, correct? Like you cannot put a say seat inside before you put the door of the car, or you first have to make the body and then only you can paint the body, and so on. There are various such kind of relationships that can be thought of, and question is that if I want to make a car, how, in which order will I go? Should I first make the tire, or should I first make the seat? Should I first put this inside or not, and so on and so forth. So, you can clearly see this is a very important problem to solve. Now, how do we do it? Here is a very interesting representation in forms of a graph. So, what do we do? We, for each of the jobs, we make a node, say A, B, C, D, E, F, G, H. Now, let us see. We have written that A comes, and here is the set of rules. See, here the first one says that A comes after B and D. So, what we do is that we draw an edge from B to A and from edge from D to A. An edge indicates that if there is an edge from B to A, that will indicate that B has to be done before A, or A has to be done after B. Similarly, if B is after C, D and E, we draw edges from C, D and E to B. If G is before E and F, then I draw an edge from G to E and G to F, and so on and so forth. And after we are done with all of them, this whole relationship that we had been represented in terms of this graph. Now, what do we want to do? We want to find an ordering of the vertices, say V 1 to V 8, in such that if V I V j is an edge, then I must be less than j. Means if I has to be done before j, then I must be before j in terms of the ordering. Now, clearly, if there exists a cycle here, directed cycle, then things cannot work out, correct? If somebody says that, see, before you take your food, you must brush, and before you brush, you must wear your clothes, and before you wear your clothes, you must take your food. If such kind of an ordering comes out, you can understand that what will I do first? There are three things, somebody is saying that do this one first and do that one first. So, that will not work. So, essentially assume that this graph is acyclic. Again, if the graph is not acyclic, we have our DFS algorithms that we can run and check whether the graph is acyclic. If not, we will again use DFS algorithm to find the ordering. So, the algorithm is that find a vertex in which there is no edge coming. So, something that is the first thing that has to be done. If the graph is acyclic, then must be some job that should be done before any other job is done, and then you do a DFS from that vertex, and according to when is it colored red, you output it. And if we find a back edge, that means we have found a cycle, we report there is a problem in the set of rules. Let us go over this topological sort quickly once. So, here is the algorithm, and here is it. We first look at, I will be a bit quick here. I first start from H, because the H does not have any incoming edges, and we look at this neighbor of H, which is G, the neighbor of G, which is E, neighbor of E, which is B, neighbor of B, which is A, and at this point let us look at the topmost vertex, which is A. A does not have any neighbor left to be taken care of, and so A is done. So, A I color red, and in fact, A I write as the last element to be done. In some sense, after everything is done, you should do A. Now, we come to B, and B also has no more edges left to be handled, and we write B. As soon as we color something red, we will output that one. Now, we come to E. At this point E, we say that okay, let us look at one edge of one neighbor of E, say which is in this case D, and we say that okay, now D D will search for two neighbors A and B, nothing, it cannot choose any of them, and at this point D says that okay, I am done. If D is done, D will output. Note that what is happening here. What is happening here is that D, when we are looking at D, all the other vertices has been done with. So, if at all there can be edges from D to all of them, there can be edges from D to B and D to A, which is in fact there, but there cannot be an edge from B to D, because if there was an edge from B to D, then it would have been found out, and then B would not have just refused, you would not have told that I am done with. So, that means that there exists no edge from D to B to D or A to D. There can be edges from the other direction. So, that is what we want, correct? We want that if something is before something, then that object should be done earlier. So, there should not be an edge like this A to D. Similarly, again say we come to the topmost vertex, which is E, and we look at its neighbor C. At this point we see that C has a neighbor to B, which is fine, but we cannot take it, and at this point C says that okay, I am done, and so C has to be output. Again here note that C has an edge to B, but is it possible to say A has an edge to C? No, it is not, because if A had an edge to C, then when we were looking at A, then A would have found out C. If A would have found out C, then C would have been marked then, and A would not have told that no, I am done with. So, there is no edge from A to C. So, thus by outputting this set of numbers according to when it is colored red is a very useful thing for understanding the ordering in this acyclic graph. Now, again say here we come to E, and E says that I do not have anything, so we will output E. Then we go to G. At this point G says that okay, I have an edge F, so it will look at F. For F it will look at these two edges. Then F says I do not have anything else to check out, so I will output F. So, F becomes red, and then G becomes red, and then H becomes red. So, thus this DFS will output me a string of jobs which says that H, let us do H first, then do G first, then do F first, and so on and so forth. Note that this is not the only option. For example, one could have told that after E I will do D and then I will do C. D and C could have been swapped. There is no reason why C has to be done before D, but that is not the point. Point is that at least one sequence have been output which is fine. So, this is what is known as the topological sort, a sorting that satisfies this topological structure of this graph. The runtime, all we did was basically run a DFS algorithm. So, it is order V plus E. Thus, in linear time we output a topological sort. So, this brings us to the end of this lecture. So, we have seen the depth first search for directed graphs, then we looked at how to find cycles in a directed graph and connectivity, and then finally, we saw the applications of DFS for topological sort. We will come back next lecture with a new algorithm for finding a spanning tree. Thank you.